have any new questions today, I thought we would just start with the homework. Like looking at the More website together. So I think we got into section 5.1 yesterday, and we got through a couple of questions about domain. So let's take another look here, just in case there was anything else people wanted to look at. We were looking at number 14, and we were looking at domain.
It was 13.
No, I don't think we did 13.
Yeah,
That's just a matter of doing the composition. But we definitely were looking here, and we did the first two. We didn't do the last one. So we could warm up doing the last one as a warm-up. And then we'll look at 15 and then move into section 5.1 and 5.2. So let's do that. The last question here. And now, folks, what I would do is I would have a sheet of line paper so that you can write all these notes down. And then when you get home to actually do this problem online, you'll have notes that you can refer to. So this is, and again, label your paper. So this is section 5.1, and this is number 14, because when you get home and log on to More, this is what your number 14 will look like too. It might not be identical, but it'll be very close. So the last part that we needed to do was h of g of x. So the first thing we need to do is simply compose it. So recall, you always start by writing down the structure of the first function first. So the structure of h is something squared minus 4. And then the function of g is 1 over root x. Now, this function right here is the technical composition. And so this is the one we want to do our domain analysis of. However, notice you can simplify it. If you square a fraction, you square the top and you square the bottom. And then when you square it, you get 1 over x minus 4. And see, looking at the simplified version, you think there's only one domain exclusion. That is a denominator. But you have to look at the original composition to notice that there are actually two domain exclusions, the denominator and the square root. Okay, so what are our domain exclusions? Remember, we had a test. We're going to start writing it down this way. So the one is you want your denominator to not equal 0. And the other test is you want the radicand to be greater than or equal to 0. But those are our two domain exclusions. We don't want to divide by 0, so you set the denominator not equal to 0. And you want whatever's inside the radical, the radicand, to be positive or 0. So let's start with the denominator. The denominator is root x, so I don't want that to be 0. For both sides, I don't want x to be 0. That's my first domain exclusion. The second domain exclusion is that I want my radicand to be greater than or equal to 0. And in that case, that's simply saying that x has to be greater than or equal to 0. So that's it. Those are our two domain exclusions. That's what we know. To draw a number line to visualize what you just found out. On the one hand, you found out you want x to be greater than or equal to 0. So I would make a closed circle and shade it to the right. But on the other hand, I don't want x to be 0. So I make that an open circle. And there's my domain from 0 to positive infinity. So now if I go ahead and go back and type that in, it should give me the right answer. My domain is 0 to infinity. And that particular answer is correct. So what questions would you like to ask about that before we move on? We'll take a look at the homework from 5.2 as well, and then 5.3. Anybody questions about domain excludes? Is this helpful to write this out in a way that it has words that actually implies what you're supposed to do? Okay. All right. Well, that was number 14. 5.2 is all about inverse functions. So again, on your sheet of paper, you might want to label. Okay, now any problems we're doing right now, these are from 5.2. And let's see, that just says select the table that represents it as a function and one-to-one. This is just asking for values of inputs and outputs. Number 4, here we go. Number 3 is a really interesting one. Number 3 is asking for the difference between how to interpret the -1, meaning either an inverse function or a reciprocal. So just take a note right here with me real quick. Recall, there's two different ways in which we do an exponent of -1. On the one hand, an exponent of -1, that means the reciprocal, which is really 1 over x. But on the other hand, doing f inverse, that means inverse, which reverses the order of input-output. So you can see there's two different ways that the exponent of -1 is used. And they represent a whole other way. They're being kind of playful here. They're saying, take f of 6 and then take the reciprocal of it. So when we write inverse function, whatever output you get, you're doing 1 divided by it. So that's what they're getting at in this problem. So if you notice, the first thing they do is they tell us that f of 6 equals 13. So that's the normal order of input-output. And then they want to know what's the f inverse of 13. So what would that be? 6. Yeah, just 6, because an inverse switches the role of input-output. So if input-output goes input 6, output 13, the inverse would input 13, output 6. But then the next question, where again they're being kind of cute, they're saying, what's f of 6 as a reciprocal? Notice, here the -1 is next to the f, here the -1 is outside. So that means reciprocal. So first I would find f of 6, which they already told me it's 13. And then it's being raised to the -1, so that's 1 over 2. So that's a good question. It's testing your understanding of the difference in the vocabulary of a reciprocal versus an inverse. And I typed in the answers, and they're correct. That was a good question. Kind of motivated me and inspired me that if I were a member of the math gang, for all you know I already am, my name would be something like Bob. That's right. Which one do I mean? Inverse, reciprocal? I'm not telling you. Right? That's how hardcore I am. That'd be my math name. All right. So here they're just talking about which tables are inverses. You're just talking about switching the order of input-output. Input-output, input-output. Here they're actually asking us to find the inverse. Now this is fun. They're saying the graphs of f and f inverse are symmetric with respect to the line defined by y equals x. It's always y equals x. That answer never changes. They're always symmetric across the line y equals x. So in this particular problem, they're just asking you to solve for the inverse, but then the answer is always going to be that they're symmetric across the diagonal line y equals x. Okay. Okay, great. This is a really interesting problem. We're definitely doing this one together. So again, this is still section 5.2, and this is number 8. So take a look here at number 8. It's a great question. It says, let f of x equal x minus 7 squared. So start by just writing it down, and let's graph it. This is a parabola, and remember, if you have a number outside plus or minus, it shifts the parabola up and down. But if you have a number inside, it shifts the parabola left and right. So which way was this parabola shifting? To the right. Yeah, right 7. It's the opposite of the sign. So I'm going to draw a quick picture here, and I'm going to say 1, 2, 3, 4, 5, 6, 7, and there's my parabola. Now, folks, does that pass? Is this a one-to-one function? Does it pass the horizontal line test? No, because the horizontal line would touch it twice. So remember, what mathematicians do if a function doesn't pass the horizontal line test? We just cover up half of it. We say, oh, okay, well, I'm just going to look at that side, or I'm just going to look at that side, because then it is one-to-one and it's invertible. So notice now the question says, find a domain on which f is one-to-one and non-decreasing. So what is non-decreasing? If it's not decreasing, it's either increasing or just flat. Yeah, so non-decreasing means it's increasing or flat. So which side is increasing or flat? To the right-hand side. And the fact that they say increasing or flat means that we're going to include the 7 at the bottom. So what domain are we looking at? 7. Yeah, 7 to infinity. So right off the bat, the domain we're looking for is 0 to, oops, it's not right at all. From 0 to infinity. Now notice how subtle this is. Notice when I type in that domain, if I type in parenthesis 7 to infinity, it marks it as incorrect. Because non-decreasing means increasing or flat. So I do technically have to include that 7. And see, that right there, that could turn a lot of people off. Right? Oh, the program is so specific. Or, oh, math, it's always so nitty-gritty. But like, it's no different than if you wrote an essay in English class and you're like, the castle, and then your teacher came along later and they were like, capitalize the T. You guys remember that? Triple underline means capitalize? Well, anyway, I mean, these things matter. Whether you're in an English class or a math class, there's always particulars. Don't blame math. Every field has its particulars. Okay, so now what we want to do is find the inverse restricted to that domain. So we want to know what's the inverse of this function if we're only looking to the right. So I'm going to Erase that real quick. I'm only looking to the right. So we had a 4-step process to find an inverse. You start by writing y equals x minus 7. You can go, I'll do this with me. You replace f of x with y. You switch x and y. And then you solve for y. So y is being subtracted by 7 and squared. So you would square root both sides. So y minus 7 equals root x. And then y is being subtracted by 7, so you add 7. And now we have y equals root x plus 7. Now that makes it look like there's just one inverse function. But notice, whenever you do a square root in the process of algebra, technically that's a plus or minus. So that means that there's actually one of two functions that it could be. We're either looking for y equals positive root x plus 7, or we're looking at y equals negative root x plus 7. And you might say, well, gosh, how do I choose which one to be the inverse? So what's one good way to choose which one is the inverse?
Try one.
Yeah, you could try one, plug the numbers in, and you can graph it. So let's take a look. We're looking for x minus 7 squared. There's the graph, and we're only looking to the right. So look how I just drag it, so I can only see the right. And then I'll graph my diagonal line, so I can see it. There's my diagonal line. So I'm looking for something that will be symmetric across that diagonal line. So my two choices were square root x plus 7. That's already looking pretty promising. Or negative square root x plus 7. Not so promising. So which one is symmetric? The green one?
Yeah.
Yeah, it looks pretty, turn your head. It looks pretty symmetric. Or the green, the purple one. No, those are not symmetric across the blue line. So we found out that yes, for sure, the function we're interested in is the positive root x plus 7. There's my inverse, not that. And how else could we have figured that out? How else, if you didn't have Desmos, how could you have known that this was the inverse and not this one? You could say plug a number in. So for instance, let's choose a coordinate over here that we know is on the coordinate. For instance, if I just move to the right one to 8, then 8 minus 7 is 1, 1 squared is 1. That's the coordinate 8, 1. So input, output, 8, 1. Input 8, output 1. So in my function, input 8, output 1. In my inverse function, what? If I input, switch there, input 1, I should get 8. So let's try them both. If I input 1 right here, the square root of 1 is 1, plus 7 is 8. Input 1, output 8. If I put in 1 here, square root of 1 is 1, negative 1 plus 7 is 6. Wrong number. So it's two different ways to have figured out which inverse was correct. Now you only have to worry about this if you're doing the inverse process and you take a square root, because then you have two options and you have to choose the right one. Okay.
It's better to pick a number on the side that you're looking at instead of like the whole thing.
Yeah, you definitely can't, because remember we restricted our domain.
Yeah, so it has to be.
So it has to be a number over here in the part of the domain that we're looking at. Yeah. Yeah, really nice, folks. Okay, so that was a good problem. Where are we here? Yep. Oh yeah, so the inverse was square root x plus 7. If I check it, it works. Now keep in mind, whether you liked everything I just did or not, you can click the video button. And then James is going to show you how to do the same thing. And look what he did. He chose the right-hand side of the parabola, and he found the domain, and then he moved on from there. Okay, let's see if there's any others from this section. Find the inverse, we did one like that. Find the inverse. Find the inverse, just more inverse questions. Now notice here, they're giving you two functions, asking you to compose it both ways. And what they're getting at, you can just,
They're the exact.
that they're both equal to x and they're called an inverse function. So that's kind of a cheap question. Like if you were just watch what I just did right now, you now know the answer to all those questions. That if you compose a function with its inverse both ways,
They cancel.
yeah, they should cancel equal x, and it's called an inverse. Okay, and then finally 13 is the same way, 14 is the same way. Yep. Okay, so that was section 5.2. And then if we just take a look at 5.3 real quick. So 5.3, now notice folks, I don't know if this shows it. Oh, wait, I can just check. Student view. 5.3. Uh-oh, they show an old assignment. Don't do the old assignment. Do assignment 5.3. I suppose I can fix that right now. That way you don't see it. Old assignment. Settings. Hide. There. Now you can't see it. Okay, 5.3. Assignment 5.3. Now, this was just all the radicals. There was only one page of square root equations that we did at the end of our notes of chapter 5. But notice that some of these are just basic questions. They're just testing your recall of square roots. So notice, like here, they're saying the square root of 144 is 12 because 12 times square root is. So we didn't do a problem like that in the chapter 5 packet, but we have talked about square roots, right? So this is just testing general knowledge. This one, simplify the fourth root of 16. Again, you can type that into your calculator, and we reviewed that a little bit. If you do the square root of x, that's really x to the 1/2, and the cube root of x is really x to the 1/3. So the fourth root of 16 is really 16 to the 1/4. And make sure you're very careful about how you type that into your calculator, that you use parentheses. Okay. Again, all of these you could do on your calculator, at least these first few. Number 6 is asking you to simplify a root. We've practiced simplifying a root a few times. So like root 45, who remembers how do you simplify a root? Yeah, you find the closest square number that goes into it. So you probably want to write down all your squares, 1, 4, 9, 16, 25, 36, 49. So 45 would be there. And you move to the left until you find a number that goes into it. And the first one is 9. So you'd say root 45 is really 9 times 5, which is really root 9 times root 5, which is really 3 root 5. So that's the process that we've used to simplify a root. And here they're saying 4 root 5, you'd enter it, I'm sorry, 3 root 5, you'd enter it as 3 for A and 5 for B. In the next problem, they ask you to simplify a root, root 90, but they just ask you to type it in directly as a simplified answer. So just to see that real quick, root 90, still the first square number that goes into it is 9, so that's 9 times 10, so that's root 9 root 10, which is 3 root 10. And the way you type in a square root is by using the letters SQRT. So that would be 3 SQRT 10. And you'll notice they tell you that. You know, they give it to you right there if you read. Okay. Let's see. And then you have some square root equations to solve. These are the types of equations we did in class. Remember, what do you have to do to the root before you can square both sides? Well, I mean, what do you have to do before you can square both sides?
Get rid of the +4.
Yeah, you have to get rid of everything else with it. You have to isolate the root. You have to subtract out the 4 and divide out the 1. Well, the 1 you can just ignore. Okay, so those are all some equations to solve, similar to the ones we did in class. This word problem we'll do together, and we'll look at graphing. All right, let's look at this word problem. Now, word problems have a particular effect on the average American, and that is to make them want to hide or eat a snack. So, but my perspective on word problems is that they're actually very interesting, and you might actually learn something, or you might be entertained. You know, so hold out that possibility that by doing a word problem, you might be entertained, or you might learn something. So let's look at this interesting one. It says, please use the formula B of L. So again, what are we on now? Section 5.3. If you didn't already label it, we're on 5.3, number 15. So they're saying B of L equals root 20. I'm just going to stop reading already. One of the first things you can always do to understand a function is to go ahead and just do a couple input-outputs, just to see how you feel about it. If the input is L and the output is B of L, just try a couple numbers and just see what happens. If I plug in 0, 20 times 0 is 0, the square root of 0 is 0. If I plug in 1, 20 times 1 is 20, the square root of 20 is about 4.3. Plug in 2, 20 times 2 is 40, the square root of 40 is about 6.5. So I'm just looking at some sample input-outputs. Alrighty then, so please use this formula to estimate the speed of a car in miles per hour. So this right here is going to be the speed in miles per hour based on the length L in feet of the skid marks. So length of skid marks. when suddenly braking on a dry asphalt road. So just imagine you're moving along on the highway, you're going 65 miles per hour, and all of a sudden you slam on your brakes and you skid to a stop, and you think about how long those skid marks are. And keep in mind, this formula only works on dry asphalt road, so not when it's raining and not on a dirt road. Right? So that's what we're saying. Now, already just think about this. The police are going to use the length of your skid marks to determine how fast you were going. Because that way, if you come along and you're like, well, I was only going 50. They can say, well, actually, based on your skid marks, you're going faster, right? So they can hold you accountable. But there is a weakness to this.
I was gonna say, when I was in high school, I had a friend, he crashed his car in our neighborhood.
Yeah.
And the way that it happened is he wasn't driving fast and then hit the brakes. He was like at a stop, and then he like hit the gas and it like spun out. And so when the cops came, they were trying to like say that he was like flying through the corner, and like I had to tell them like, you know, he would like at a stop and he like hit the gas really fast, and that's when he spun out.
Interesting.
It's crazy.
Yeah. So I mean, the police tried to do this analysis to figure out what was happening. But there's a problem with this, because let's say you're driving along and you realize you're about to drive into a tree. You hit the brakes, you skid for 1 foot, bam, you hit the tree. So if you only skid for 1 foot, you think, well, gee, my skid length was only 1 foot. I was only going 4 miles per hour. But that might not be the case. You could be going 100 miles per hour, only hit the brake just in time before you hit the tree, and you were actually going 100 miles per hour, and the 1 foot long skid mark does not accurately reflect how fast you're going. So there is a limitation to all of this, but hey, you know, the police are trying. They're trying to recreate the scene of an accident. So anyway, how does everyone feel about this function? You know what we're talking about? We're talking about skid marks and trying to figure out how fast we're going. So at the scene of an accident, a police officer measures the car's skid mark to be 121 feet long. So what do we know so far? Yeah, that was 121. So approximately how fast was the car traveling? So now remember, functions, you can only do one of two things. You can input a number or set it equal to a number. Right? Those are the only two things you can do. Plug a number in or set it equal to a number. So what am I going to do with my L? Plug it in. Because it literally is telling you it's an L value, so the appropriate thing to do is plug it in. So we go ahead and say V of 121 equals root 120 times 121. And that'll give us whatever the answer is. So that's root 2420, which is 49. Now, again, this whole notion that your skid mark was 121, like what would that even mean? That you're driving, you hit the skid marks and you skid to a stop, but then you didn't hit anybody. You know, so if that really is the full length of your skid mark, then that means you didn't hit anybody. Unless like you went, and then right at the last little second, you were like, ding, right? So what does this speed tell you? Since your skid mark is actually shorter because you skidded and then hit someone, this actually represents what? The minimum speed you were going or the maximum speed you were going? Yeah, the minimum. What this test really tells the officers is, hey, when you hit that person, you're going at least that fast, but probably you were going faster.
Speedometer says 100.
Correct. Okay, so that's the first question. Next, one of the people involved in an accident says he was traveling at 48 miles per hour when he braked. How long in feet should his car skid mark be? So, okay, so now we're saying that our speed is 48 miles per hour. What should I do with that number? Yeah, set it equal to it. Now, how do you know that we're not supposed to plug it in? Why not plug it in? Yeah, because it's a miles per hour, it's not a length. So it'd be inappropriate to plug it in. Okay, so instead we're going to do root 20L is equal to 48. And then you do a little bit of algebra and you square both sides. And so that would give us 48 squared. Whoops, 48 squared. So that's 20L equals 2304 right off to 20. And so the skid length is 150. That's how long his skid mark should be. Okay, well that's the problem. Now, everyone, just reflect for a moment. Wasn't that interesting? Wasn't that a little bit kind of interesting to know that, the police use models like this to figure out how fast people were going, and that's how they hold people accountable as to whether or not they were line or not. It's pretty interesting. So word problems can be entertaining, and you can learn something. Okay, now how about graphing? They're asking us to graph a square root function. First of all, what does a square root function look like? Everybody, what does a square root function look like?
Depending on your.
Either one of you. Go ahead, Gabe.
So say if you take a parabola and just flip it.
Yep, exactly. And Hector?
All numbers that are, like all numbers except for the, all real positive numbers except for basically, yeah, basically.
Okay, yeah. Yeah, it's a sideways parabola. And in fact, if I also graph negative square root x, we literally get the entire sideways parabola. So if you just turn your head, boom, that's the parabola. Okay, so we want to graph a square root, and what we're going to do is transform it. By transform it, I don't mean optimus prime. I mean, move it up, down, or right, left. So how far did this one go up or down? Down 2, and then this right or left? Left. So your tool is already, then I go down 2, and then left 1. I put my first dot. That's the origin of my square root graph. So now I just have to choose one more coordinate. So how do I find one more coordinate to put on the graph? Plug a number in, exactly right. This is why it's so important to understand that a function is an input-output machine. You have total freedom to input a number and see what it outputs. So I have this function, f of x equals root x plus 1 minus 2. What would be a nice number to plug in? Yeah, 3. Why 3? Yeah, 3 plus 1 is 4, and 4 is square rootable. You can plug in 3, you can plug in 8. 8 plus 1 is 9, and 9 is square rootable. Choose a convenient number. So f3, thank you, Omar, would be 3 plus 1 is 4, root 4 minus 2, and root 4 is 2 minus 2, which is 0. So if I input 3, I should output 0. Therefore, the coordinate is 3 zeros on the graph. So I'm just going to go to 3, 0, put my dot, and it's graphed. Now check it. And it's correct. I got half of it right. I still have to put the domain in. What's the domain? Remember, domain is how far a graph goes left to right. So how far to the left does it go? Yeah, -1. And how far to the right does it go? Infinity. There we go.
Does it include it?
It does include it. That's a great question. How do you know if it includes it or doesn't include it?
I could see it is a bracket.
Oh, yeah, yeah, it is a bracket, yeah. And why do we know that it includes -1? Can I plug -1 into this? I can. Because -1 plus 1 is just 0, and I am allowed to square root 0. That's not a calculator error. And so input -1, output -2, there is an actual coordinate. Yeah. Oh, yeah, so was. All right. Well, folks, I realized that was, I don't know, kind of fast. What time did we start? Well, we did 30 minutes. We did 30 minutes of questions from the homework. What do you think? Should we do that more often? Now, again, I realize I went fast, and that's because I was trying to do 5.1, 5.2, and 5.3. What if in the future, because I was talking about this with my other class, what if we set aside 10 minutes at the end of each class to take homework questions? Would anyone like that?
Yes.
Okay. And so then your responsibility is to come with homework questions ready to go. Now, of course, if you have a homework question, I hope you've already emailed me, because then I've already emailed you back. But you can still come up with questions that you want to ask. And if nobody has any questions, I'll just choose some that I think are fairly interesting. But hopefully you can all, you'd be able to just tell me, yeah, let's do this one, let's do this one. Because I realize that when you do the homework, it's going to apply the things we've learned. And it might apply in a way that we didn't literally do in class. So it's asking you to apply things in new situations, which is truly the challenge of all education. Is you learn a certain number of things from a textbook or a teacher, and then you have to apply it in a new way. So it can be tricky, but I'm happy to help. All right, so I think I already told you both of these jokes. So I need to give you a new joke. Lee, you have any jokes today? Let me see. Lee had some good ones yesterday. Now, folks, I will tell you a joke right now. Now, today we're starting chapter 6. In fact, let me show the calendar. Today we're starting chapter 6. Chapter 6 is really exciting. really exciting, like mind-blowingly exciting. Like this is going to change your life to learn this new field of mathematics called logarithms. Now, who studied logarithms already? Do you remember from high school a little bit? Okay, sweet. So you might already have a little bit of experience. Hopefully, what we do in this class is going to bring even more enlightenment to you, and you're going to feel like, oh wow, this logarithm thing is pretty interesting. Okay, so here's my joke. How does a lumberjack dance? With logarithm. Yeah? No? All right.
What is the tallest building in the world?
Lee, what is the tallest building in the world?
The library. Got the most stories.
Good one. All right, so here we are, folks, March 27th. We're going to start chapter 6. We have all next week to do more, and then the test is the following Monday. I've already posted online on Canvas announcements the practice test and the solutions for the practice test. So you can already go ahead and go download those and start working your way through it. All right, so everybody grab a hold of this one. I have copies up here. I'm assuming everybody got a copy. This is so much fun. This is so interesting. I mean, you're going to want to go home and share this with your friends, your family. Once you have kids, you want to tell your kids about it. If you don't have kids, you're going to tell somebody else's kids about it. I just need to want to move this over so I can actually write on it. There we go. There we go. Sorry that my screen's a little slanted, but idea. All right, folks. All the way up at the top there, I want you to notice that I have 3 equations. X squared equals 9, 3 squared equals x, and 3x equals 9. What I'd like you to do is just go up there right at the end of 3 branches of mathematics. Hey, I'll get a chair now. Oh, I am always.
How exciting when you do
Go ahead.
it.
So let's consider the expression 3 squared equals 9. Okay, 3 squared equals 9 is a pretty simple looking expression. I mean, this is, it's an exponent. You multiply 3 times 3 equals 9. It's just a fact. There's nothing to solve. It's just right there. It's a true statement. So what I want you to notice then is that I have 3 numbers here. 3, the 2, the 9. And what I'm going to do is one at a time replace one of them with the x. So the first thing I did is I replaced 3 with the x. Instead of 3 squared equals 9, it's x squared equals 9. Then I replaced the 9 with the x. Instead of 3 squared equals 9, I wrote 3 squared equals x. And then I replaced the 2 with the x. So instead of 3 squared equals 9, it's 3dx equals 9. And depending on where you put the x, you're looking at a different branch of mathematics. So let's look at the first branch of mathematics. I replaced the 3 with the x. How do you solve for x here? What'd you say? Square root, right? And so if you square root both sides, go ahead, just show a little scratch work there. If you square root both sides, then you cancel the 2, then you get x equals plus or minus 3. And what did we just do? What's this process called? Algebra, right? I mean, that's the whole field right there, algebra. Something that humans have been doing for thousands of years. Algebra. Okay, so that's one whole branch of mathematics, is how do you manipulate x? Now, notice, that's when x is the base. Right here, I put x into the base number. And if you just consider any equation that has x as the base, like ax squared plus bx plus c, x is the base of an exponent. Here, x is the base of the exponent 2. Here, x is the base of the exponent 1. And here, x is the base of the exponent 0. So every polynomial is algebra. X is the base. Every rational function, any equation with x. Well, no, where x is the base. That's algebra. Okay, next. 3 squared equals x. How do you solve for x? Yeah, you just square the 3, right? And so what's that called when you just take a bunch of numbers and compute them? Arithmetic. That's right, arithmetic. All right, nothing fancy there. It's just arithmetic. So another word for arithmetic is PEMDAS. So basically, this represents elementary school, and this represents junior high, high school, and college. Right? Okay, now the last thing, 3 to the x equals 9. First of all, do you know what x should be? 2, right? Because 3 to the power of 2 would be 9. 3 squared is 9. So what do you call that when you solve for an exponent? Logarithm. Yep, it's called a logarithm. Logarithm. A logarithm is when you solve for an exponent. So anytime your variable is in the exponent, you just solved a logarithm. So I'm going to give you all a quick feeling of success. 5 to the what equals 25? Does anyone agree? 5 to the power of 2? Boom, you just did a logarithm. You might not realize you did a logarithm, and it might not feel like you did a logarithm, but you did a logarithm because you solved for an exponent. Anytime you solve for an exponent, it's a logarithm. Now, how about this? What about 3 to the what equals 27? No, 3, because 3 times 3 is 9 times 3 is 27. What about 2 to the what equals 128? All right. I mean, that might push our ability to do it in our head. But you can still do it in your head, because you could start saying 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, and times 2 is 128. So what's x? 7. Okay, all 3 of those problems were logarithms. We didn't use a logarithm yet, but solving for an x is what logarithms is. Okay, so now that we know that there are 3 branches of mathematics that come simply from considering with taking powers of things. So every number that you see up here right here, by the end of today or maybe tomorrow, I expect you to have all those answers memorized. Consider it your new times table. You know how when you were a kid you had to memorize like multiplication facts? I think it'd be very easy for you to memorize all these, and I'm about to show you how. Ready? So first of all, 2, 3, 5, 10. These are the important ones. 2, 3, 5 are the smallest prime numbers.
You pull down the center.
Oh yeah, sure. There you can see it. And 10 is a good number because it's base 10. That's our decimal system. What are they?
I was just thinking.
Oh, okay. Yeah, base 10 is our decimal system. So let's go start with 2s. We're going to start with the ones that are obvious, which is raising a number to a positive whole number. So 2 to the 1 is 2. And then 2 squared would be 2 times 2, which is 4. And 2 cubed is 2 times 2 times 2, and which you can just take the previous number and multiply by 2 again. It's 8. And then 2 to the 4th, again now, you can do this with your fingers. And I encourage you to try. 2 times 2 is 4, times 2 is 8, times 2 is 16. Or you could just say 2, 4, 8, 16. And do the doubling process in your head. But it's helpful to use your fingers to keep track of where you are. So 2 to the 5th. So like try it. If you don't want to say it out loud, just think it. 2 times 2 is 4, 8, 16, 32. So the answer is 32. Now, if you don't know all those off the top of your head, 2, 4, 8, 16, 32, spend some time with it. Actually sit down and try computing. That normally puts it into your mind much better if you just take 16 and multiply it times 2 the old-fashioned way. 2 times 6 is 12, carry the 1. 2 times 1 is 2 plus 1 is 3, 32. So the more you actually practice it, the more these numbers will become familiar to you. All right. I had a buddy, all the way back to childhood. He told me one day that when he's bored, standing in line, driving, traffic, he'll actually just start doubling 2s. That's what he does. And you'll see how far he can get. So he'd be like 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8,192, and he would just keep going like that to the billions. He's a nerd, obviously, but that's what he would do. So you could at least practice walking around campus.
Did you ever beat him?
Did I ever beat him?
Since you mentioned him.
Oh, I don't know that I ever went higher than him. I don't even know how high he went. It was just the idea of doubling. So start practicing. Definitely want to know your 2s. Okay, so now let's turn around and go back the other way. Now, as you go up, you'll notice, what were you doing? Every time you went up a number, what did you do? You multiplied by 2, right?
Multiplied by itself, actually.
So you're multiplying by itself, yeah, but you're multiplying. So now, you also notice the exponent. What was the exponent doing? 1, 2, 3, 4. Well, you were adding 1, right? So now let's turn around and go the other way so that we can ask the question, what's 2 to the power of 0? What's 2 to the power of -1? What's 2 to the power of -2? So if we go down now, what did you do every time you went down? You divided by 2, right? So 32 divided by 2 is 16. And 16 divided by 2 is 8. And 8 divided by 2 is 4. And 4 divided by 2 is 2. So logically, the next answer, 2 divided by 2 would be 1. So that's a definitive reason for understanding why anything to the power of 0 is 1. So now keep going. What happens if I divide by 2 again? And notice now your exponents you're subtracting by 1. So 5 minus 1 is 4, minus 1 is 3, minus 1 is 2, minus 1 is 1, minus 1 is 0, minus 1 is -1, minus 1 is -2, minus 1 is -3. So as we go down the list, what should the answer be? 1 divided by 2 is, the fraction, 1/2. And then go again. What's 1/2 divided by 2? 1/4. And then what's 1/4 divided by 2? 1/8. And 1/8 divided by 2? 1/16. 1/16 divided by 2? 1/32. Now, you can see very obviously that you only have to memorize 1/2 of this list. Because the top, those are the numbers you have to know, 1, 2, 4, and 16, 32. And the bottom is just all the reciprocals. Which you'll notice, again, anything raised to the -1 or a negative exponent, that's a reciprocal. Not an inverse, but a reciprocal. Okay, so there we go. Those are your powers of 2, at least to 2 to the 5th. And again, by tomorrow, I expect that you should be memorizing all this. You might not have it perfectly memorized, but you want to at least have a familiarity. That if you were like walking down the street and you saw the number 32, you'd be like, hey, isn't 32 a power of 2? I feel like that's the power of 2 I've seen before. Okay, so now let's try 3's. 3 to the power of 1 is 3. So 3 squared is 9, and then times 3 again. And now here's where it might break down a little bit. You might need to practice 2 times, type it in the calculator, multiply by hand. 27 times 3 is 81. And then 81 times 3 is 243. Again, if you don't have it memorized completely, you can always just jot it down and multiply it out. Or you can use a calculator. But again, you want to have some familiarity. Like 243. I recognize that number. I think that's a power of 3. Which is it? Is it 3 to the power of 4, 3 to the power of 5? I'm not sure. Let me check. Okay, so now turn around and go back. What's anything to the power of 0? Yeah, for the reason we just mentioned. Because as you go down, you divide by a trig. So then you have 1/5, 1/9, 1/27, 1/81, and 1/243. Okay, so powers of 5. You can all do these because you're familiar with our money system, which has quarters. So I'd like you to genuinely try to do these in your head. So first of all, 5 and 1 is 5. So what's 5 squared? 5 times 5? 5. So from here on in, you're computing with quarters. Don't shout out the answer yet, but try to do it. What's 25 times 5? How much money do you have if you have 5 quarters? 5 quarters? That's $1.25? That's 5 quarters. Yeah. Now this next one is fun. How much money do you have if you have $5.25s? You've got $5.25s. So you've got $5 and you have 5 quarters. So the $5 is $5. And what's 5 quarters? 125. So $5 plus 125 is 625. Okay. Now even more fun. How much money do you have if you have 5 $6.25s? Okay, you can do it. I know you can do it. You have 5 $6.25. So if you have 5 $6, how much do you have? You have 5 $6. That's $30. And then 5 more quarters. So that's 30 plus $1.25, $31.25. Okay, so again, memorize these numbers, become familiar with these numbers, and now we turn around and work our way back down the list. So 1 1/5, 1 1/25, 1 1/25, 1 6/25, and 1 31. Now, how much money would you have if you had 5 $31.25s? You can do it. I know you can. All right. So how about tens? Tens, again, tens are the base of our decimal system. They're the base of our metric system. There's a good reason why we use 10. So 10 to the first is 10. You'll notice the exponent is 1, there's 1 0. 10 squared is 100, the exponent is 2, there's 2 zeros. 10 cubed is 1,000, the exponent is 3, there's 3 zeros, and so on. So that's very convenient, and that's why in the late 1700s and 1790s, the French government made the metric system a decimal-based system using powers of 10. Because it's so elegant, it's so easy, not at all like our silly imperial customary system of 3 feet in a yard, 5,280 feet in a mile. I mean, it's ridiculous, honestly. The imperial customary system is crazy because every unit is different and you have to memorize every different conversion. Whereas in the metric system, when you say kilometer, that's just a kilometer. And kilo means 1,000, so it's 1,000 meters. You know, very simple. Okay, so now turning around and going backwards, 10 to the 0 is 1. Now here you have to memorize how many times the decimal moved to the left. So 10 to the negative 1 is 0.1. The decimal moved once to the left. 10 to the negative 2 is 0.01. The decimal moved twice to the left. And 10 to the negative 3 is 0.001. The decimal moved 3 times to the left. Notice it's important that you change how you memorize it, because if you just think 3 means how many zeros there are, now you'd be wrong. Because it's 0.001, there's only 2 zeros, even though it's a negative 3. Negative 3 represents how many times you move the decimal to the left. So 10 to the negative 4 would be, if you wanted to start with 1, it would be 1, 2, 3, 4. And you fill in zeros. 10 to the negative 5, you start with decimal here, and you say 1, 2, 3, 4, 5. And you fill in zeros. That's actually the same rule for up there. Like if you want 10 cubed, you start with the decimal where after the number 1, and then you go 1, 2, 3, and you have 3 zeros. So in fact, when you have a power of 10 system, the exponent literally tells you how many times to move the decimal, which again is why France adopted a decimal-based metric system. Because then to convert from, say, a kilometer to a centimeter, you just move the decimal. Whereas to convert from an inch to a mile, you need a calculator. Yes, I could? There you go. And yet they didn't give us a metric system. Well, they did, but we didn't accept it. We are apparently one of only 3 countries in the entire planet Earth that doesn't act. And I forget. It's some Far East Asian country, and then Liberia and Africa. The metric system is merely our preferred system, but you know that in America we don't use the metric system. How tall are you? 5 foot something, 6 foot something. I mean, our culture is imperial. It's not metric. If somebody told you that they were 1.6 meters tall, you'd be like, what are you, an idiot? Right?
It's kind of funny since we try to get away from it.
Yeah, well, imperialism is the practice of Britain taking over everyone, and America and other countries. Okay, well, so we've done it. Again, try to memorize those numbers, become familiar with them. And now that we have some familiarity with taking a number and raising it to a power, what we're going to do is ask a very interesting question. And even though, well, yeah, we're going to do 10 to the x equals 50. So here's a question. 10 to the what equals 50? We're going to try this problem. Now, everybody need a calculator out. Take out your calculator. Everybody needs a calculator. You definitely cannot just sit and watch this. You have to participate. And you also need a sheet of paper. So what I'm going to do here is give you a historical problem that motivated the advent of logarithms. Now, first of all, logarithms were essentially introduced and written about for the first time by John Napier, a Scottish mathematician in the late 1500s. It was his life's work. His life's work was to create and establish this idea of a logarithm. So that's how far back it goes. He created the logarithms. I'm pretty sure he even introduced the word logarithm. Logarithm. That's not right. No, that's it. So again now, what does logarithm mean? Did we write it up at the top? Solve for an exponent. Yeah, anytime you're solving for an exponent, you're doing a logarithm. Whether you know it or not, you're doing a logarithm. So we're going to ask this question, what is 10 to the x equals 50? Now, first of all, does anybody know? 1.7? That's pretty close, over. 1.7 is pretty close. Everybody type in 10 to the power of 1.7. So again, you need a calculator out. 10 to the power of 1.7. Is Omar close? It's pretty close. Close enough for government work, as they say. Zing. All right. So, but 1.7 wasn't exactly right. It was a little too big. All right, 10 to the 1.7. 1.7 was a little too big. So, well, actually, this is kind of awesome. I'm watching you guys. A good half of you are already kind of playing around in your calculator. You trying to find the answer? Well, Larry, what are you doing? You trying to find it? What number are you trying right now?
Well, I tried 4. I mean 5. I tried 6 and then 5.
Oh, 10 to the 1.6, and you tried 10 to the 1.5?
Yeah.
Okay, very good. You tried 10 to the 1.69? Not close? Oh, not close to this. So this is good. I mean, you're already kind of playing with the idea of what trial and error means. You just try things until you get close. So what I want to give us is a method that will refine our answer and give us as many decimals of accuracy as we wish. So you start with 1 decimal of accuracy, then you go to 2 decimals of accuracy, and then 3, and you keep moving your way forward, more and more accuracy. Now this approach that we're going to use is called the sandwich technique. Sandwich technique. Now I know normally most of us use the phrase sandwich technique to describe what we do at midnight. Go to the kitchen and make a sandwich, and we eat it. But the sandwich technique means, here's an answer we'd like to find. 10 to the what is 50. And what we're going to do is sandwich this between 2 answers we know. So one thing I know for sure is that 10 to the 1 is 10, and 10 to the 2 is 100. And I've just sandwiched my answer between 2 things I actually know. So this is our first sandwich. I just made a sandwich. So I've got, just to be especially corny here, I've got my slice of wheat bread, and then I've got my very tasty veggie patty in the middle there. So there's my sandwich. Now, this is not very good, because right now all I know is that the answer is between 1 and 2. So what number should I try between 1 and 2? Now, notice what I'm going to do here. I want a number between 1 and 2, so it's helpful to put another 0 at the end. So I need a number really between 10 and 20. Yeah, you could always just start by going to 0.5. You could just say, well, I don't know, so I'm going to go to 1.5. And that's not bad. For the purpose of this demonstration, let's go straight and say, let's just guess 10 to the 1.5. So I'm going to write down 10 to the 1.5, and you might want to write small, because we're going to generate a lot of possibilities. So now you take your calculator and you say 10 to the power of 1.5, which is 31.6. Too big or too small? Too small. So you go up a decimal, 10 to the power of 1.6. And now again, instead of typing it all in every time, you can hit second enter and just backspace and change 1 digit. So 10 to the 1.6, I got 39.8. Too big or too small? Too small. So I go up to 10 to the 1.7. Now you notice this is a very simple algorithm. You're not doing a lot of thinking, you're just trying different numbers in order. So now 10 to the 1.7, you get 50.11. Too big or too small? Too big. We just found our next sandwich. Here's our next sandwich. 10 to the x, you don't have to write this again, but 10 to the x equals 50 is in between that sandwich. Okay, so now we look, it's between 1.6 and 1.7. So again, you tack on an additional 0, so you can say to yourself it's between 60 and 70. So what's the number between 60 and 70? You can try 65. Now in this case, we could be a little strategic. 50 is really close to 50.1, and it's very far away from 39. So you could try a number closer to 70, like 69. So let's try that now. I'm going to go ahead and type in 1.69 and see what I get. So 10 to the power of 1.69, we're trying to find our next sandwich. 10 to the 1.69 is 48.97. And well, the next number we already knew was 10 to the 1.7, which was 50.1. So that already is our next sandwich. So between 1.69 and 1.7, we should have our answer. So again, you tack an additional 0 at the end, and now we're looking for a number between 690 and 700. So what's a number between 690 and 700? Yep, 695. So we try it. So we're going to do now 10 to the power of 1.695. Now you'll notice this process is really exciting, right? Like you're on the edge of your seat right now. You're like, oh, this is so exciting. Let me keep doing it. But it is just a trial and error method. So let's go ahead and try that. 10 to the power of 1.695. That's 49.5. Too small. We're going to do 10 to the power of 1.696. Now, this chain is a little long because I have to keep trying and writing them. 10 to the 1.697. That's 49.77. Oops. There we go. That didn't work. 10 to the 1.6.
I got it.
You got what? What, the whole answer? Or the next sandwich?
It's the next sandwich, so.
Oh, okay, yeah. So that's 49.
1.6.
Let's try it. Aha! Indeed. That's 50.003. We have our next sandwich.
I get to a smaller than that.
Yep. Now, a couple of considerations before we keep going. Maybe we shouldn't call this the sandwich technique. Maybe it should be the panini technique. No? Anyone? A baguette? No? Just sandwich is fine.
A croissant.
A croissant. Okay, so how do we go between 0.698 and 0.699? Again, you tack on an additional 0, and you say, okay, what's between 80 and 90? And probably just 85. So then we would proceed, and we'd say, okay, I'm going to do 10 to the power of 1.6985. What? Oh, I do? Okay, well, let's find out. So that's interesting for that to have happened. So it's 6985. Oh, no, that's 49.94. Yes, I need to go higher than that. So now I'm going to do 10 to the power of 1.6986. Let's see what that gives me. That's 49.95. 7. Somewhere there, 1.6987, 49.96. This could take a while. It's not 88. It's not even 89. Oh man, so I'm just going to skip to the end here. If I go to 89, I'm still not quite there. That's 49.99. And then I know from the previous result, it was 1.6990 was 50.003. So there's my next sandwich. It's somewhere between 6989 and 6990. So again, what do? I tack on an additional 0, and now I'm looking for a number between 890 and 900. So what's the number between 890 and 900? Yeah, 95. 895. Yep. So then you say 10 to the power of 1.69895, and try again. Yeah, so we're going to stop here in a second, but 1.69895. That's 49.9976. I got to try one more because we're so close. So 69896.
7's not even
6 is not it.
7's not even
7's not it either. 8, it is 8. Okay, so we need to go between 7 and 8. Okay, so the 7 gave me 49.999995, and then 8 gave me 50.0011. Okay. Well, other than the fact that you're excited right now, do you see what we're doing? We're generating more and more decimals of accuracy. Now, if this were government work, or if we were talking about money, we're already there. This rounds up to $50. That rounds down to $50. So a decimal answer of, let's go ahead and write it down, everybody. 10 to the power of 1.69897-ish is 49.995. Awfully close, right? Now, how many actual decimals of accuracy are there in the true answer? As many as it takes. In this case, how many decimals? Infinitely many. Okay, so this is a thankless task. How long would you be doing this? Forever. It's infinitely many long. It's infinitely many digits. Okay, well, so back to John Napier. John Napier did this. I want you to imagine. John Napier did this, not just for 10 to the x equals 50. He made a whole book of 10 to the x equals every integer from at least 1 to 100 off the top of my head. So he did 10 to the x equals 51, 10 to the x equals 52, 10 to the x equals 53. And he made a big, long book giving the decimal answer to all these numbers. And I don't think he stopped at 1 to 100. I think he actually went 1 to 1,000. Something crazy. And do you know how many years it took him to make this book? 20 years he spent writing this book.
How old was he when he started?
I don't know how old it was when he started. But keep in mind, what was he doing? He was creating a new branch of mathematics. So just imagine the social pressure he experienced where people would be like, hey, John, come out to dinner with us. He's like, no, man, I'm going home to keep writing my book. They're like, what book are you writing? Finding Powers of 10. Like, that's a rough uphill struggle that he did. He was creating and establishing an entire new field of mathematics by writing this book, spending so much years of his life. But the fact is, every calculator in the world now has a what button? A log button. So his effort was successful, and he created this new branch of mathematics in which we have a way to solve for an exponent quickly and easily. So everybody, here's the exciting thing. We want to know 10 to the what equals 50. Everybody take your calculator right now and simply type log 50. And say thanks, John Napier, as you do it. Log 50. What do you get?
6, 9, 8, 9, 7, 0, 0.
So that's the answer. Were we on our way? 6, 9, 8, 9, 7? We were on our way. You know, we had a little more work, and that's not even the whole answer. There's infinitely many decimals in that answer. Now, really exciting. Everybody now, do 10 to the power of, and type in that decimal. Do 10 to the power of 1.69. Oh, what do you got?
50.00000.
And you know what's crazy? My calculator tells me 49.9. Some of your calculators say 50.0. Happened in the same class. No, it happened in the other class too. Our calculators must be different. Like I have an 83. You also have an 83.
I missed
Maybe
zero.
No, that's the thing. You didn't 6989704. 69897. You didn't mistype it. I didn't mistype it. No. Well, hold on. We got the same answer. 49.9. We got.
Oh yeah, oh yeah.
Yeah. Who got 50.0?
I missed the zero.
Are you sure? Double check. What did you?
Yeah, I got
What do you go
40.
back? The 49. Okay. Oh, you did. Okay. Well, then whoever did it in the last class must have typed it in wrong. Here, I thought all our calculators might be different. Okay. So all that said, folks, we now know that we have a button on our calculator that will calculate the appropriate power of 10 to equal a number. So look at this next row of options here. There is a simple way to calculate what power of 10 will equal a given number. The log button on your calculator. So if you want 10 to the what equals 50, you just type log 50. If you want 10 to the what equals 90, you just type log 90. What? Absolutely. Oh yeah. I mean, this is just introduction. Like we're about to study logs for like the whole week and that. Okay, so if you want 10 to the what equals 100, well, first of all, everybody, 10 to the 1 is 100. 2. So everyone type log 100 in your calculator. Try it out. What's log of 100? 2. Yeah, log of 100 is 2. Okay, and then likewise, if you want 10 to the what equals 500, it's log 500. And it tells you the power of 10. Now this is wonderful. I know my phone went off. We're about to take a break. This is wonderful. So let's just recap what we've talked about here. The field of logarithms means solve for an exponent. Okay? Anytime you solve for an exponent, you are doing a process called logarithms. Now, we just learned that we have a very nice button on our calculator called log, and that log button will solve any problem that is 10 to the power of something equals a number. Now, that's very helpful and all, but we're not just going to come across problems that are 10 to the power. What about problems like 2 to the power of x equals 20, or 3 to the power of x equals 15, or pi to the power of x equals 5? How do we solve those problems? There is no button on your calculator that does base 2, base 3, base pi. Your log button only does base 10. So we have a lot of theory left to generate. There's a lot of tools and skills and new vocabulary and new ideas that we have to kind of plod through before we can solve a problem as simple as 2 to the power of 1 equals 20. But by the time we're done generating all this theory, you'd be able to take any base to the power of what equals any number. And you'd be able to solve that quickie-do on your calculator. Okay, let's take our break. Time is 1:36. Let's come back at 1:46.
Yeah. What's up? Check.
Oh, no.
It's gonna be easier watching you.
As soon as my
Tends to be, started. Who does that remind you of? Oh, yeah.
Don't worry, people. It's 100% me.
no. At least I don't see it.
Hey, Omar.
Is there a new thing on those corrections for the midterm?
Well, it's not a midterm, it's just a test, and I just made a recommendation of a week. You know, that way it's fresh in your mind. It's, you know, get it done, move on. So hopefully you could turn it in by the beginning of next week. Super.
Hey, Augustus, do you want to tell the camera what you just did? You were sitting up like this. Oops. See, nobody did. I just sat up on my own. You sat up on your own. Good job. Good job.
Ay, no me quiero sentar. Pues, ¿por qué lo borraste ahí? ¿Qué? Pues porque fue. Ay. Pero mira, ah, quisiera ver.
¿Qué?
I have really short legs, and that's what Estamos en la medida. No muy mucho ni importa. That way you can get like a tall boyfriend. Or you can get a short boyfriend and then the average is like 5 years old. You put high heels on. That's what I like. That's what I like. Porque my friends are tall and they're killing me. Y yo, cayéndome de jeta. Yo sí, bueno, a veces. A veces no. Yeah. Oh god. Mom's about to turn 40. Oh, no, I don't want to. Because I want to get away. I do feel like
I have a question. What age
Mhm.
do you think is middle age?
I feel like middle age. Really? Oh, I think 50.
I think 50.
Yeah.
Because 60 to 8, no, that's 70 to 80 is kind of.
All right, folks. Now we're going to try applying this new definition and learning the vocabulary that goes into it. It is a little awkward at first. You know, you're learning a whole new vocabulary, kind of like you're learning German or Russian, or even more so, you're learning a language that has a new alphabet. So like, yeah, like Klingon. No, like there you go. That's a great analogy. Like it's one thing to just learn a Romance language because you're using the same alphabet, but like to learn a new language that's in a different alphabet, whoa, then you're in a whole new world. So let's approach this as if you've never seen it before and talk about what the vocabulary would be. So